Every day, students and faculty walk into the AAB without thinking twice about the air they're breathing. But what if the air was quietly working against them? That's the question that started this project, and the tool that helped us answer it, was it a sensor, a spreadsheet, or a site inspection? It was a digital twin of the entire building, and it changed everything about how we understood the problem.
All right, so I'm Samuel with the Digital Twin team, and the topic we were dealing with was VOC compounds in the air. So as you can see in this room, we've got all kinds of things that put off VOCs. We've got paint, we've got welding, we've got soldering, we've got glues. All of these things put off volatile compounds that are poisonous to people in the air. And so the problem we had to solve was, why is the building having these build up in these brand new spaces? And so we built our model to model the system, all the HVAC units you see in the room, to see how all of those things would be moving through the air and how they could potentially link to other rooms in the building.
A digital twin is a virtual, data-connected replica of a physical system, not just a 3D model that you can look at, but a structured, navigable representation of how the real system is built and how its pieces connect to each other. For a building, this means capturing every room, every duct, every vent, and every mechanical system and the relationships between all of them. It means being able to ask questions like, where does the air from this room go? Or how many exhaust vents serve this space? If VOCs are present here, how do we get rid of them? These are questions you can't necessarily answer from a floor plan. You can't answer them from sensor data alone, but you can answer them with a digital twin, because the twin shows you the system the way the system actually works. We built ours using Metro, a knowledge modeling platform by Tenet 3, and the digital twin's ability to do all of that, unify the data, reveal the relationships, and make the invisible visible is shown very clearly through our models.
Of course, a digital twin is only as good as the data behind it, and getting that data was its own a challenge. For sensor access, we navigated facilities department across 5 separate visits just to identify the right people. The Director of Labs, Liz Humphrey, oversees the sensors. Capital Project Admin, Nina Scott, holds the building plans. Both were absolutely essential. Neither was easy to reach. When we finally got the sensor access, the sensors were given inaccurate readings, and specific data we needed wasn't even available to us yet. It wasn't until the second semester that 2 of our teammates secured the proper permission to pull usable data. Then came the building plans, over 600 pages of engineering prints. We combed through all of it, isolate the HVAC and exhaust system we needed to model. We say this because it matters. Building a digital twin isn't just a technical exercise, it's people exercise as well. Every door we knocked on, every permission we chased, every page we reviewed, that was all in service of feeding the twin accurate, real data. Because a model built on incomplete information doesn't reveal problems, it hides them.
So where does this leave us? This leaves us with a living model that will update and grow for future semesters as students add more data and add more features to it. A model that allows us to view problems as they occur or before they can occur. This allows us to plan ahead and add on to the building as we need.
With the building's Revit files in hand, we converted them to IFC format, an open source standard that lets building model data be parsed and structured across platforms. That conversion was the bridge between raw engineering files and a working digital twin. We split the team across 3 floors of the building and the exterior. Each group was responsible for mapping the HVAC and exhaust systems in their section, every vent, every exhaust port, every air handler connection, and feeding that data into one shared model. Because the digital twin is collaborative by nature, each team's work layered directly into the others. We weren't reconciling separate files at the end of the semester. We were building one unified picture of the building together in real time, with every new piece of data making the whole model sharper. This result was something that this building has never had, a complete digital twin of the AIB's air system, navigable by floor, traceable by system, clear enough that someone who's never read an HVAC schematic in their life could look at it and understand how air moves through this building. The twin didn't just store data, it made the relationship visible, and that visibility is what turned months of scattered information into one single moment of clarity.
So here's what the digital twin showed us. Every room in the AIEB that produces significant VOC levels has a minimum of 2 exhaust vents. 2. Rooms with confined chemical processes have even more. Let that sink in. That pattern holds consistently across the entire building, except for one space, and that is the outer garage, where the Baja SAE formula car lives, where students run a gasoline-powered engine, handle fuel additives, and perform regular mechanical work. It has one singular exhaust vent, just one, not 2, not 3, just one. It's a tiny one. That car is arguably the highest single source of VOC emissions in the entire building, in this giant, massive building, and it has less ventilation coverage than nearly any other comparable space in the building. This is a finding we never could have reached by just walking the building, reading through 600 pages of blueprints, or staring at sensor readings in isolation. It only became visible where all of that data was unified inside the digital twin. The twin connected the physical layout, the mechanical systems, and the sensor data into one coherent picture. And when you can't see the whole system at once, a gap that glaring becomes impossible to miss. When ventilation can't keep up with VOC production, gases build. When a door opens to grab a tool, whether to take a break or move between spaces, those gases travel with the people moving through the building in different rooms, and that's why VOC levels were spiking. A design gap in one space, hidden in plain sight until the digital twin made it visible.
We brought these findings to Liz Humphreys. In our second meeting, we walked her through the digital twin directly. She could see the ventilation gap in the context of the full building, not as an isolated data point, but as part of a complete picture. That made the difference between describing a problem and showing it. She committed to helping us move it forward. That's one of the most important things a digital twin does, that a report or a spreadsheet can't. It meets stakeholders where they are. The facilities director doesn't need raw sensor logs. She needs to see clearly where the building is failing and why. The twin delivered that conversation in a way nothing else could have. We also connected with Dr. Anton, who introduced us to the building's vibration sensor network. Sensors attach the structural beams of the AIB that record movement and structural activity through the building. These sensors, activated through a graduate student named Wyatt, represent exactly the kind of additional data stream a digital twin is built to absorb. As more sensors come online and more building data becomes accessible, the twin grows more accurate, more complete, more useful. The digital twin isn't a finished product, it's a living model. It gets better with every new piece of real-world data connected to it.
So where does this leave us? The immediate recommendation is clear. Exhaust capacity in the AIEB garage needs to increase. Matching it to what other high VOC spaces already have is the most direct fix. And it's a recommendation we can make with confidence, backed up by a complete model of the building rather than just a guess. But the larger takeaway is about what this building now has that it didn't have before. A digital twin that gives every future decision maker a single unified picture of how this building's air system works and where the gases are. Facility staff, lab directors, engineers, future student teams, they all now have access to that shared model. That doesn't just go away when our project ends. As the building changes, systems updated, spaces repurposed, new sensors added, the twin can change with it. It becomes a long-term tool for understanding and managing the building, not just a snapshot of what we found this year. What started as a VOC monitoring problem became a data problem, became a modeling problem, and solving the modeling problem with a digital twin gave us the answer to everything else.
The AIB is where a lot of us spend most of our time. It's where we build things, test things, break things, and learn. The people in this building deserve to do all that in air that's safe. We came asking, why are VOC levels spiking? The digital twin gave us that clarity to answer that question. Thank you. So, this was a really fun project.
Yes, learned a lot.
Yeah, it was hit a lot of snags along the way, but we figured it out.
It was really nice solving a real problem for facilities that's going to have real impact for years to come on the campus.
Yeah, it was pretty cool. We're actually generally proud of it. It was a fun project, and it was pretty cool to see that we actually have stuff that's going to be useful for the people.
I'm sure in the future others will find it really helpful, and it'll be a good way to like educate like anyone that wants to learn about the building and the HVAC. So yeah.
But yeah, we've been the digital twin team. It was really cool to learn about solving a real problem for a real client and get some experience as we get into the workforce.
Yep. So I'm Dalton Sloan.
I'm Samuel Hartman.
And I'm June Hunt.
And Donald and Brock couldn't make it for the outro, but they were just excited as we are.
Yes.
Cool.
Thank you.
Thank you.